introductions. Today we have the U.S. Department of Energy Water Power Technologies Office joining us. We have Elaine Buck, who has spent the last 12 years focused on the development and testing of marine energy projects. She is a technology manager in DOT, or not DOT, DOE. She leads the technology-specific system design and validation portfolio, which focuses on research and development associated with utility scale and water deployments of marine energy devices. She holds various technical advisory roles for organizations such as Ocean Energy Systems and provides oversight on WPTO-funded projects at DOE's national laboratories, with the goal of delivering solutions for moving the marine energy sector closer to commercialization. She is active in standards development at both the domestic and the international levels, and she serves as a co-convener for conformity assessment of standards at the International Electrotechnical Commission. And Elaine recently received the 2023 IEC 1906 Award, which recognizes individuals who help significantly advance these activities. And I am going to ask my colleague, Michelle Carnes, to please admit participants from the lobby because they are popping up on my screen very rapidly.
We got
And
it.
then, thank you. And then our second speaker will be Dana Makowski. Dana is the Environmental Technologies Manager in WPTO with Elaine, and she leads strategy, management, and execution of their environmental R&D portfolio for the hydropower program. Her background includes over 20 years of experience in program development and project management, technology R&D, and commercialization, laboratory and field research. She works across sectors with partners in national labs, industry, academia, small businesses, and tribal partnerships to support technology transfer. Her research focus areas of interest include fish passage, aquatic connectivity, developing monitoring technologies for sensitive species, sensor systems, and eDNA, and advancing sustainability science to improve environmental outcomes and siting of renewable energy systems. So thank you both for joining us. I will turn it over to you.
Thank you.
Thanks so much. Dana is actually going to be speaking first, so I'm going to drive the slides for her. So Dana, if you want to kick off and just tell me when you want me to move the slides.
Elaine?
Yes.
I don't see the slides anymore.
Okay, let me stop and reshare.
Okay, thank you. And while we're getting that going, thanks so much, Patricia, for inviting us here. I appreciate the opportunity to share about the Water Power Technologies Office. I got the slides back. Thanks, Elaine. Been having a bunch of technical issues today, and my camera just seems to stop working. So if there's something wrong with the audio, the chat seems to still be working, so let me know. I'll do my best. All right. I do want to point out, while we're still Water Power Technologies Office, our previous overarching pillar, the Office of Energy Efficiency and Renewable Energy, has been rebranded. So we are now in an office called the Office of Critical Minerals and Energy Innovation, and a lot of the renewable technology offices from DOE are now also in that pillar, with some other great offices as well. All right, next slide. So what does the Water Power Technologies Office work on? First of all, we are the R&D and innovation branch for water power. We have hydropower and marine energy programs and a burgeoning interest in the nexus between energy and water. The hydropower program looks for a lot of different types of opportunities to add hydropower and pump storage. This may include very low environmental impact projects, modernizing the existing fleet, or developing pump storage. There's also interest in adding power to infrastructure such as canals, and some industry trends towards hybridization of systems, so utilizing existing hydropower infrastructure to add other benefits such as storage. The Marine Energy Program works with wave, tidal, river, ocean current, and ocean thermal conversion. And we work across the technology readiness scale. We work with really low technology readiness ideas, like from idea, concept, all the way to deployment and commercialization. Next slide. This is a slide of the budget starting in fiscal year 2008 through present. And what you can see here is our budget has grown over time. So there's been additional investment in water power. The bars on the bottom, the darker color is the Marine Energy Program, and the lighter blue color at the top is the hydropower program. And so we've been able to work with a lot of great partners. You get a lot of different projects developed. And I think the number of topics and the number of ideas and the numbers of the different types of technologies we've worked on has increased. So it's been a really great experience. I've been with the office for 10 years. I've seen a lot of this development happen. Next slide. All right, so now we're just going to focus a little bit in on the hydropower program itself. I mentioned a little bit of this, but these are the core technologies or types of opportunities for hydropower that we're working with. The majority of adding power to the grid in the last decade has been upgrading existing facilities for capacity. There have been some new small builds, and there's really tremendous opportunities for storage and just improving what we've already got deployed. Dams have hydropower dams have a average life of around 100 years, I'd say, and so we have quite a few different dams that still could be modernized and both produce more power, but also get another 30 to 50 year term out of a federal license, for example. Next slide. Okay, and this is a map from a Oak Ridge National Lab, which is one of the DOE national labs that we work with closely. It shows U.S. hydropower, and the different colors are different types of ownership, and there's a key on here at the bottom, but these are just different types of hydropower dams. I want to point out that in the U.S. there's over 90,000 dams, and only 2,252 are power plants. But hydropower is making up over 6% of the electricity capacity. And like I mentioned before, we have added gigawatts in the last decade. And this could take the form of powering non-powered dams, some small additions from canal hydropower, some new small projects, and from these capacity upgrades. We also have 43 pump storage plants, which provide the vast majority of the U.S. utility scale power. Next slide. So what are we seeing? I mean, you can't really look at the news without seeing there's this increased energy demand. Some of this is from data centers and AI. We're seeing a lot of the tech companies being more interested in hydropower and supporting them in relicensing. So there's a financial opportunity for some of the owners to make partnerships with tech companies. We're seeing a lot of opportunities for increased collaboration and watershed planning. There's a large interest in fish passage, removing dams that don't serve a great purpose anymore, like legacy infrastructure that doesn't have benefits, maybe can't be powered and is creating more problems than it's solving. And there's a lot of interest in thinking about what transmission is going to need to look like to serve all of this energy demand. Another huge thing to point out is there's both federally owned hydropower, and this is just over 200 plants. Army Corps, Bureau of Reclamation, Tennessee Valley Authority are good examples of those federal owners. But there's the rest of the fleet, the couple thousand other dams are privately held. So about half of that fleet is up for relicensing. And this is really the time when all the change happens. They're setting the conditions of a new license, they're making improvements, they may be getting new turbines or generators, and going through a comprehensive environmental review as well. And like I said, the big trend really is hybridization, or maybe thinking about how you could add on pump storage to an existing plant. And so these are things that the owners are considering the cost and the benefits for as they're trying to figure out which choice to make. We're seeing a lot of challenges in the Western U.S. The hydrograph has been changing. There's a long-term drought. What this means is that reservoirs are becoming lower, and it's putting a lot of risk on the hydropower. And that we're seeing a large increase in developing new technologies for energy capture, like things like putting hydropower in pipes, or developing turbines that work really well in really low height dams, so that you could potentially add power for dams you want to keep. Next slide. And this is just another map from Oak Ridge National Labs HydroSource program that has split up different watersheds and looked at when we're going to expect to see those the Federal Energy Regulatory Commission licensed hydropower plants coming up for relicensing. And it's scaled by capacity. So it's just another way of illustrating when things are going to happen. And as it goes from a blue color to an orange color, that's over, sorry, I'm saying it backwards. As it's going from the orange to the blue are later in time, and the orange and yellow projects are probably, they probably have almost all the information required at this point, or are working actively to get it. So this is a huge challenge. If we, for some reason, didn't have these plants, you can see it's a lot of megawatts that we might lose. And in some areas, there's, a cluster of small plants which have a more challenging time sometimes financing improvements. And so with this program at the lab, we have a huge wealth of information, environmental information, information about the equipment in the facilities, et cetera. So if you're interested in this kind of thing and data resources, I would definitely check out HydroSource. I can put the link in the chat when I'm done presenting. Next slide. I think that we commented on a lot of this, but it's good to have these things up here. So like I said, our office has a lot of different types of projects that we fund. The grid resilience portfolio is a very large one. There's some new work into cybersecurity, which is becoming an increasing interest. Most of what we're doing is working in that innovative technologies, design, evaluation, and commercialization space. We have a bunch of other supporting science and innovation, improving forecasting, some very advanced models coming out of our labs that are now available, and we've been working with federal and non-federal partners so that they could use the outputs of the models to evaluate risk to hydropower. But a lot of what we're doing is just working to advance this across the spectrum sets of technologies that can help us meet these goals of modernization, adding power, improving the environment, and making things more safe. Next slide. This is a slide that is highlighting a project that's really focused in on non-powered dams. Because there are so many non-powered dams, it's been a huge thing to consider. If you have a dam that's in place, it's providing irrigation or flood control or something like that, provides a lot of benefits to your community. It might be another added benefit if that dam is going to be there to add power. And so there's a whole suite of tools that we've developed primarily at our national labs. And I'd say Oak Ridge National Lab and Pacific Northwest National Lab, and Idaho National Lab as well, have really, and I'm probably forgetting someone, but they've really invested a lot in helping people understand the attributes of the dams, where they are, and to provide tools so that people can run analysis like this one here, where some set of criteria were put into a tool, and it's showing you like which ones seem like the most beneficial for those criteria. And I think this is just an example of a model run with what the tool would look like, where people were saying like, we want to identify where we can retrofit dams, prioritize opportunities, and I think they said like, where can we increase the role of clean energy in the grid with this scenario. That's an example of the type of tool that the national labs are building for this specific topic, but we have quite a bit of investment in this area and have provided a lot of support to industry and using the tools as well. Next slide. This is a relatively new initiative, the Hydropower Testing Network, and HYDN for short. This is an idea that we've been thinking about for a long time at the Energy Department, because we don't really have a hydropower specific test bed. We have hydropower dams that, we may be able to work with the owner or operator with to utilize to deploy technologies, but there's a lot of risk to that. No one wants a science project at their dam that, is important and has like potentially like safety or like could create an electric outage if, like someone's working on it. So it can be sometimes really challenging to partner with owner operators. Other times it's a little bit easier, like they may really want some data or be really interested in technology and have their hand up to work with us. But the idea here is to create a network of labs and facilities potentially, where we can have a continuous stream of funding to help help people with innovative technologies find a testing facility, to get them just a little bit of data to move forward, to help create an innovation ecosystem to match technology developers with facilities that can help them complete testing. And so we've just in the last year or so launched this network. So we've gotten people to say like, hey, I have this testing capability. This is how much it is to utilize it. And we've gone through the first round of evaluating proposals for partnering. And I will also put the link to this in the chat for you to look at in case you may be interested. But this is a new initiative that we're looking to evaluate its effectiveness to deliver test results faster. Next slide. This is something I've worked a lot with at DOE. Some of the largest focus for the environmental portfolio is improving downstream fish passage when fish are migrating or moving downstream. If there's a dam that has hydropower turbines, often they're required to screen or to put other fish protection technologies on the dam to avoid them from being entrained or moved with the flow of water through the turbines. But we've spent a lot of time developing tools to improve the biological performance of turbines and to be able to design turbines that are safer for fish and don't harm them. And so this is an example of, we've had quite a bit of funding in this area, and we've worked with both industry to enable them to uptake these design principles, and also the national labs and others to develop the foundational information to support the design standards and tools. Next slide. And yeah, the pump storage hydropower is really related to our grid portfolio. We've both learned that the industry is very interested in valuation of flexibility or the storage, the ability to potentially store water over seasons or shorter periods of time. to support the grid. And so we've developed quite a few tools to help better understand the value of storage or pump storage to provide long duration energy storage. We provided a variety of technical assistance to industry to help people understand choices they may have. Would a battery provide that flexibility, or would you consider upgrading to add some pump storage, which is really like a water battery. Like it just works from you're pumping water between different elevations and storing it to be released into flow through turbines. And so you can use an existing dam as the lower reservoir, so to speak. And then there's been some really cool innovative ideas. This QuidNet geomechanical pump storage idea was looking at pumping water into abandoned wells. I believe they were from oil and gas or fracking wells potentially. But so there's also been some really like creative ideas of how you could create like micro storage almost that we've invested in and helped the companies to establish some baseline feasibility. Next slide, that might be it. There might be one more. Oh yeah, I guess this is a great thing to point out. We're often working with partners. We have a lot of different partners on the hydro side. There's this group of, they call them the visionaries. There's a group that's actively participating and mapping out a 50-year vision for the hydropower industry, and it's really an industry-led effort that our national labs support. I talked a little about the Hyden Hydropower Testing Network. I work with broad groups of industry agencies, resource and regulatory agencies, NGOs, to host environmental and industry summits to highlight research needs and to help with partnering for environmental efforts. We have had a few different memorandums of understanding with the different federal owner-operators, and more recently with some of the research institutes in Norway. Norway has a lot of both hydropower and pump storage, and it's been an interesting opportunity to work internationally with them. And then I myself participate with the Fish Passage Task Force, which has the 13 agencies that either own or operate or evaluate or have something to do with hydropower. Maybe they have some regulatory authority over them. And so we've helped to coordinate R&D and to provide a flow of information. But we're also always working with the national labs. There's quite a few just DOE programs that help support lab intellectual property through partnering for commercialization. Next slide.
All right.
All right, and turn it over. Thanks.
Thanks, Dana. I'll try to get through some of our marine energy slides a little bit quicker so we have some time for questions and answers. So again, thank you, Patricia, for inviting for me to come in and talk about our marine energy side and the challenges that we're seeing as we scale up in the industry. So we've had a long history of being able to deploy smaller scale devices. Marine energy we're in research and development to wave energy converters that are at the watt scale all the way up to megawatt scale. And on tidal, it's usually around the kilowatt scale all the way up to megawatts that we've been focused on. We've had 21 devices in the water here in the United States. That is covering 18 developers and over 9 states. So our technology plan has been really started since 2008 when the marine energy team was set up. But Europe is considered much more advanced. I actually came from the European Marine Energy Center in Orkney, Scotland, where I was there for 10 years, where we were testing wave and tidal devices. And they have been much further advanced in terms of their number of deployments and the years that they have been deploying open water tests within Europe. Marine energy testing infrastructure. This is also a very huge component of our program. We put in a significant investment into a wave test site called PacWave. It is in its third budget period, meaning it is going to be fully commissioned in 2026. This will be the first grid-connected accredited test facility for wave energy technologies in the United States. It's on the coast of Oregon and will accommodate up to 20 wave energy converters in 4 separate test berths. So these grid-connected test berths will be able to provide an electrical cable back to an onshore substation where that is connected into the local utility. And there is a power purchase agreement that's also being finalized right now with that local utility. So they're able to generate revenue from the grid connected technologies that will be tested at PacWave. We also have a fantastic organization called TEAMR, which is Testing, Expertise, and Access for Marine Energy Research program. This actually is a group that accelerates the viability of marine energy by providing developers and researchers access to a network across the U.S. of testing facilities and testing experts. So this could be through universities as well as our national laboratories. So in 5 years, TEAMR has grown its network to include 45 different facilities and supported over 200 projects with 25.4 million of technical access and expertise that's been supported. I think the main difference is that this is not funds that are going directly to the marine energy developers, but it's the funds that are going to help them to access the expertise and the infrastructure at the national labs. We also have very specifically for tidal. Tidal is also much more well advanced than wave energy in the United States. And we had the largest I think it was a NOFO funding opportunity that was in 2023. And this was the Tidal Energy Research Development and Demonstration Pilot Site. I was the technical lead on this, and we have 2 applicants, one in Washington, and this is with Orcas Power and Light Cooperative, OPALCO, and they're proposing to deploy a tidal energy turbine in Rosario Strait in the San Juan Islands of Washington. That device is expected to produce up to 2 megawatts of power, and the team aims to develop this pilot site that will provide renewable power to a local power supply for the islanders, as well as for additional electrification of other assets. So they're looking to electrify ferries around the islands, and this opportunity with providing tidal would be able to generate that. The second applicant or tidal project is in Alaska, and this is Tidal Energy Research Development and Demonstration Pilot Site. This is with a company called ORPC, and ORPC aims to deploy 2 tidal energy devices at the Cook Inlet in Alaska. This is off East Foreland on the Kenai Peninsula. The device is expected to be capable of producing up to 1 to 5 megawatts of power, and they want to demonstrate the feasibility of tidal energy projects in Cook Inlet, which is the largest tidal energy resource that we have in the United States. These 2 projects are currently in a down select, so I can't allude to who we think is going to come out on top, but we're really excited in 2026 to be able to announce the applicant who will be awarded the majority of the funds to continue development of the tidal pilot site. So as I understand it, sort of the objective for the presentation was to identify where most of the challenges are for marine and wave in regards to our access to shipyards. So how do we scale up? So our main challenge is that we have non-standard over-engineered designs. So wave, this is mainly on the wave side and lesser to the extent on tidal. So what that means is that we have a multitude of different wave energy converter types in the wave space, but on the tidal space, we actually have either floating or seabed mounted tidal devices. These bespoke designs, they're primarily being built for the very first time, and they're intended to operate for years with minimal maintenance, leading to very high safety factors. And so some of them have been overbuilt, which adds to weight and complexity as well as cost. There is very little manufacturing experience in the United States to manufacture wave and tidal devices that have been built to full scale. So the opportunity is to grow the industry expertise. There is a great need for the size of these devices for a heavy lift capacity. So we're very interested in understanding at the ports what high capacity cranes are available. And there's a real need for specialized load handling equipment for these devices to put them either from the quayside into the harbor or the port, or to be able to tow or to take those devices out to the site where they're going to be deployed and connected, for example, in Oregon at the PacWave site, or either in Alaska or Washington for the tidal projects. There is a great need for deep water access, so some devices require an adequate water at the quayside, and some other means for transporting those large components to the install site. So we're talking about very, very large vessels that are needed to be able to handle these devices. The present market size is very limited, and so we are looking to impact that by working with oil and gas companies as well. Except the problem is that most of the oil and gas is down in the Gulf of Mexico, and to try to bring ships up either to Oregon or even around to some of the to Alaska is really cost prohibitive, especially on the day rates that the oil and gas companies are able, or I should say that the marine supply chain is able to charge. They're still looking at oil and gas prices and payments compared to research and development, which is really, really difficult to cost in. This is just a great example of one of the wave devices that were manufactured in the United States at Viger. This is in Oregon. This is the size of the device. This is considered the stern, and this would be the bow. The generator is actually on top of it. This is an air turbine. This is an oscillating water, where water is actually intake into the base of the device and funneled through at high pressures that turns the turbine, which actually then creates the electricity. This is a grid connected device, and it was deployed out in Hawaii. This has had a lot of challenges there was a tow. We had to tow this vessel all the way from Oregon to Hawaii, and during the transit there was some damage. We don't exactly know where or how the damage occurred. Or we know where, but on the device, but it was significant enough to where it had to get to Hawaii, and there had to be significant repairs done in Hawaii. And it was a challenge in Hawaii because the original fabrication and manufacturing occurred in Oregon. So trying to find the same steel as well as the people who had the experience was a real challenge. But this is just to give you a size and dimensions, and I'm not sure exactly on the weight on this device, but I could get you that information if you're interested. So I just wanted to, hopefully this will work. This is a YouTube video of what it's like on the tidal side. So these are two devices. This is a seabed fixed fixed a mounted turbine. And this is what is planned for the Rosario Strait out in Washington. It's the size of a small airplane, and it has two blades, and these wings actually retract down into the tidal flow. It's a really very cool piece of equipment that is now been deployed actually in Scotland at the Orkney test site. So let me see if I can get this to work, because it demonstrates the size of these devices and the ports and where they've been deployed. So I might have to get through some ads here. Apologies. Thumbs up if you can see this. Thank you. So this is Orbital, and this was at Dundee Port in Scotland. I think that's a really good example of the challenges that they have with moving around a device and actually getting it off the quay side and into the water. This was a simple tow to the site in Orkney, but other devices don't have that luxury. I'm going to stop sharing for 2 seconds so I can get back to the slide deck. Okay. All right. So this is the International Energy Agency Ocean Energy Systems Infrastructure report. Actually, it's really a technology report that talks about the sort of the vision globally for what we are trying to deploy by 2050. So we are looking to deploy 300 gigawatts of wave and tidal by 2050. The split is about 180 of wave energy and 120 gigawatts for tidal. This is the equivalent of 680,000 jobs that would be created with a GVA of $340 billion, 500 million ton reduction in carbon emissions. And within this report, so these are all the targets, there is a chapter on infrastructure and future development. I can put the link to this report as well in the chat, and you can go in and read in greater detail. But the growth of the factor would require about 100 dedicated ports installing up to 300 megawatts per year by the mid-2040s. So the consideration from all the way from fabrication to decommissioning needs at these ports will need to be in place. So the report goes into a little bit further detail. So they estimated that the existing ports would need to be upgraded. So manufacturing and fabrication space would be around approximately 3,000 hectares of new infrastructure needed. The laydown space of 1,000 hectares of new infrastructure, the quayside berth, the length and the draft is going to be vital and important, because we're not just deploying just that one device that I showed you that video of. The idea, and that was a 2 megawatt device, the idea is that we would try to deploy an array of tidal devices, so 1 to 2 to 3 devices. And then on the wave side, we could be deploying, the goal would be to be deploying up to 1 megawatt or more. And most of the wave devices at the moment are around 250 to 500 kilowatts. So you then can understand the number of wave devices that we would have to deploy. The access to the channel and the width and clearance is key. So you saw that Ocean Energy device that was at the Vigor manufacturing site. they need clearance, and trying to, maybe deploy or tow that under a bridge, they may not have that clearance. So ports with clearance is going to be huge, as well as the depth, to be able to put these devices into the water and tow them out to site. Okay, so that's all I had on the wave side. So that gives us almost about 15 minutes for questions and answers. So please just, I guess I'll hand it back over to Patricia, and she can lead that part of it.
Wonderful. Thank you. Thank you, Elaine, and thank you, Dana, for those presentations. They were very informative, and I am going to go ahead and pause the recording.